Okay, good morning and welcome to the VOLTHA 2.14 Techinar. I am pleased to introduce VOLTHA TST co-chairs Sirkant Erlidaria and Abhilash Laxmeshwar, who will be presenting today. After the presentation, there will be time for audience Q&A, but in the meantime, feel free to drop any questions in the chat. With that, over to you, Sirkant and Abhilash.
Thank you, Michelle. So first, I'll go over the agenda. Just a second. Yeah. So today's agenda, probably some of us already familiar with the project, and the information might be repeat for some of you. But we will also look at the things which are specific to the VOLTA 2.14 release. I'll start with the SIBA reference design and how VOLTA fits into it. And then we will look at the VOLTA and its architecture and the important features. And then we'll jump over to a typical VOLTA test setup that you can set up in your lab, how you can use VOLTA in your environment. Also, we have CI/CD systems. Also, I'll touch on that too. Then Abhilash will go over the release notes and the important features coming with the new release. And finally, we will tell about how you can join and contribute to the VOLTA project. And at the end, we'll have a questions and answers session. So let's start. SEBA is based on the desegregation idea. So I want to spend a few minutes on looking at what is the desegregation idea in terms of SIBA. On the left, you see a traditional loyalty, which is a chases-based loyalty. It has, line cards, and it has a specific software which is produced by the vendor, OLT vendor. And the idea with SEBA is disaggregating all of these into multiple components and separate out the POM part. What is shown here as a white box, and this is the POM part handling the traditional loyalty. So it's a pizza box design. And also there are fabric switches also as a white box switches. So those white box fabric switches can aggregate multiple OLTs. And also with a standard compute service, you can deploy the application logic into the servers. So the OLT only serves only a thin software part, and the most of the application OLT logic could be in this compute nodes. These compute nodes, even they can be public clouds like AWS, or it could be operators' private data center. And this gives you the ability of easier management, of course, and also easier software updates. And most importantly, you don't rely on any specific software coming from a specific vendor. Moving on. And looking into the SIBA reference design, and if I start from the top, there's a carrier automation platform which encompasses what operators have. This could be directly the operators' OSS/BSS systems or any intermediary systems of the operator. This talks to SEBA northbound interface, which is a standard interface that is also evolving with the project. Below that, the network edge mediator. Let me grab the laser pointer, yeah. Network edge mediator. Over this, you could interact with various pieces of the broadband network. So you can see it's working with VOLTA, its fabric applications, BNG applications, and also getting FCAPs from the network devices. The device manager here manages the management plane, and the VOLTA controls the control plane of the PON network. Um, so also on top of SDN controller, um, this is these applications here like VOLT, DHCP, MCAS, Mac Learning, these are part of the control plane, and these applications are deployed into the SDN controller. So as I said earlier in the disaggregation idea, most of the OLT logic, OLT application logic can be installed in this VOLTA applications. Below that, we have VOLTA. You can see that you have the typical PON devices like OLTs and ONUs, and they are connected to the fabric switch. They all aggregated to this fabric switch, and also those fabric switches are connected to the compute nodes so that these applications can be installed in this compute nodes, can be communicated with each other. So VOLTA currently is the red box here. VOLTA currently focuses this red box, and this device manager, we only, oh, by the way, all of the source codes is open source in this red box. The only exception is the device manager. We don't have the device manager implementation, but we defined the interfaces. Moving on to the next slide. So let's take a deeper look into the VOLTA architecture itself. Starting from the top, you can see there are two SDN controllers. VOLTA Go controller is introduced in 2.12 release, and this is the last release that will release with ONOS. It is decided that ONOS will not be a part of the release. So from 2.12 to 2.14, we use this period as a transition period. And VOLTA, basically the VOLTA Go controller, probably Abhilash will talk on that more, but a VOLTA Go controller is the re-implementation of existing ONOS applications to overcome some shortcomings of the ONOS SDN controller, especially regarding performance and scalability. Below the SDN controller, we have the OF agent, which basically stays as a proxy between ONOS and the VOLTA core. It acts as a protocol converter between the VOLTA interface, which VOLTA interface supports gRPC protocol, and ONOS, it supports the OpenFlow protocol. So OF agent acts as a proxy. But with the introduction of VOLTA Go controller, the requirement to have such a proxy is also not needed because VOLTA Go controller directly speaks the native gRPC protocol that VOLTA Core supports. And as you can imagine, this is also another performance gain. Other than that, we have on the left the VoltCTL. It's a command line interface to interact with VOLTA. This is mostly used for debugging or when we are developing new features and when you don't always have the controller running, you can use the VoltCTL. And not shown here is the VOLTA Protos repository. That protos are defined in another open source repository called as VOLTA Protos. And you can implement any client using those protos because that's protos actually defines the northbound interface of VOLTA core. So you can implement something similar to VoltCTL or any other client you would like to have. Below the VOLTA core, you can see there are different adapters, and the communication between these adapters are also, again, via gRPC. That communication protocol is also defined in the VOLTA protocols itself. the VOLTHA Open OLT adapter on the right. Uh, this is the adapter, Open OLT adapter available in the community's code repository. And the other open source adapter is the VOLTHA Open ONU adapter. This implements the OMCI stack for the ONU communication. And on the left, the specific vendor adapters is shown, but we don't have any specific vendor implementation in our repository. So this is to show that apart from the white box OLTs, some vendor can bring their traditional OLT and implements its own adapter and communicate with VOLTHA. So with the same code base, only with a specific adapter, you can control your traditional OLTs or different OLTs at the same time. So you can have a mix of OLTs in the same system. In case of the white box OLT, you also have another component, which is depicted here as the OpenOLT agent, and this runs on the white box OLT itself. So this agent talks to the OpenOLT adapter using the OpenOLT proto. It's also defined in the VOLTHA protos repository. Depending on the white box OLT in this case, it's a Broadcom-based OLT that we support right now. And it uses the Bell APIs to configure various things on the device itself. On the right, you can see that there's a depiction of Kafka, and the Kafka bus is used for all of the FCAPS management. All the adapters, VOLTHA core, other components can sense their alarms, events, and their metrics to the Kafka message bus. So if you have an implication on the northbound or if you want to integrate with operators or SSPSS systems, you can directly talk to this Kafka message bus, or you can have another intermediary level to make some protocol conversion between your OSS/BSS systems. For the DMI, we talked a little bit about the DMI. As I said, we don't have the device manager implemented as an open source, but we have the DMI protos as described in the proto files, and this is based on a standard IETF RFC. It is 8348. So there are various OLT vendors that implements their own specific device manager. So you can work with their OLTs. The last point I want to talk about is about the scaling, and I will come to it to the next slide. For the scaling, how we achieve it so far is that we brought the concept of VOLTHA stack, each VOLTHA stack composed of at least one instance of VOLTHA core and adapters. And in case of using ONOS, also an instance of an OF agent. We have the centralized ONOS cluster set up as highly available that can support connecting multiple VOLTHA stacks. In case of VGC or the VOLTHA Go controller, if you use the VOLTHA Go controller, then the ONOS and OF agent doesn't come into this picture, and VOLTHA Go controller VGC along with VOLTHA Core and with the adapters, they form a VOLTHA stack, a single VOLTHA stack. And those VOLTHA stacks are independent of each other. So if you want to run more number of OLTs, so you can spin up as many VOLTHA stack instances you would want, but this is the only limitation is the number of or amount of resources like your CPUs and memory that is available in your system. But each of these VOLTHA stacks still has some commonality in terms of the infrastructure. For example, you can use the common Kafka for FCAPS and events. And also we have a database. We support two different databases. It's actually key value stores. etcd is the original data store that we were supporting. So we also brought the Redis support. So you can even use a single instance of Redis or etcd, or you can have a common etcd or Redis that supports all of your VOLTHA stacks. That depends on your deployment. Also, it is possible that on the right, even you can connect to a single VOLTHA stack multiple OLTs. This is also another option. So as you can see, the system is elastic enough that you can fit into your deployment model. So coming to the VOLTHA feature set, you can of course read it. I need to be fast. So the new feature that we brought with the current release is the multiple NNI support. Abhilash will talk on that. So these are the current VOLTHA feature set that we are supporting right now. And for the example VOLTHA test setup, in the lab, if you have a physical OLT and physical ONU devices, you can connect them with some of the simulators. So in the lab, we have a DHCP server running on a Linux server and also VLC to test the multicast support. So you can simulate the BNG here. Also, using different Linux instances, you can install some software into your Linux machines and then simulate the RGs, or you can plug into real RGs if you have. So compute nodes here. If you use Kubernetes, then you can install the VOLTHA on this compute nodes using the Kubernetes and Helm. That is also possible. Other than that, we have an important simulator which is called as BBSim. It is software-based, and if you don't have any physical devices, you can even test out using the BBSim if you want to implement a new functionality on top of VOLTHA. And we use the BBSim extensively in our lab tests, also in our CI/CD systems. And moving to the next slides, as I said, the VOLTHA community in Linux Foundation has its own CI/CD implementation so that any patch requests and committed code are tested automatically. This helps us for the verification, and we try to make sure a new code committed doesn't break any existing functionality. Sorry. This CI/CD environment run BBSim as a simulator, and also we have physical devices in the lab too. And on the right, you can see some interesting links. You can look at our Jenkins jobs and the test codes, also the pod configurations, and the BBSim repository here for the simulator. So Abhilash, I'll leave the screen to you and stopping sharing so you can share.
Okay, hello everyone. So I'll go over what all we have in the 2.14 release and also in 2.13 because we didn't have any Techinars for 2.13. So I'll be covering one important part of 2.13 release, which is the VGC. So VGC is a controller, sort of which runs alongside ONOS, but most probably a replacement for ONOS going forward. So why the replacement is ONOS by itself was very resource hungry and not really good at scaling well. especially if you want to scale with thousands or 10,000 or even 100,000 subscribers per phone. So the amount of resources taken was like very unrealistic, and also the performance numbers were not up to satisfactory. So hence we introduced VGC, which is very lightweight version of what ONOS does. It consumes less resources, especially CPU and also the RAM. And it supports as of now the DT workflow, and we are working on the TT workflow. Eventually we'll get it. That's on the VGC. Now the next 2.14 release support what we have is the multiple NNI support, which is as of now there only with VGC. Now what multiple NNI is, we can have multiple NNIs uplinks on an OLT, but they're not really like a redundant links. They're like static links. It's just that the subscriber bandwidth are spread across multiple upstream NNI ports. So they are configurable per subscriber. Like you can have a few subscribers configured to a NNI1, few to NNI2, few to NNI3. There's no lag as now, no redundancy. It's just two separate links which wherein the subscriber traffics are being shared. And moving on to the next feature, we have the on-demand diagnosis for ONUs and OLTs. So we already have PM for OLTs and ONTs. Like every 15 minutes, the metrics are already being sent onto the bus. At times, we would also need to fetch on-demand statistics. And this is what we have supported via VoltCuttle. So as of now, the VOLTHA Protos exposes or defines interfaces wherein you can go and get specific counters from the OLT, specific counters on NNI, specific counters on the ONT, and also T-count related counters, also gem related counters, and all the gems across T-count. So there are a lot of counters now for debugging purpose, because we don't want to go to OLT every time to debug, and this would be very helpful in debug. And we'll keep on adding if at all we see any further counters which we need to add. And yeah, that's on the counters part. Next is an important one, wherein this is a ONU reboot call flow optimization. So what the earlier used to do is whenever there is an ONU LOS or an ONU reboot, so the flows, we used to remove the flows for the ONU. So the flows basically in OLT are removed, the flows basically in ONU are removed, so the flows across the control plane is removed. So considering, if we consider a scale environment, wherein a lot of ONUs go for a reboot, in that scenario, the amount of resource consumption is very high. Okay, and the configurations, what we really do for the ONTs are literally static configurations. The configurations once we do, right, we don't want to disturb it until and unless the subscriber is out of our network or the subscriber unsubscribes his subscription. Till then, the configuration will remain and has to remain. So that is why this optimization made sense. So what we do is, once an ONU LOS is there, there are flags which we have said we can enable or disable this feature. So we ask the controller not to clean up the flows once the ONU is done. So what this will do, the OLT side flows are there. The ONU side, of course, the ONU has gone down, the flows, the config, the mid the MIB configurations may be lost, but the configurations are there in the ONU adapter. Okay. Now, once the ONU is back up, ONU adapter will be notified from OLT adapter that ONU is back up. Now, if there are any flows already configured for the ONU adapter goes ahead and configures only for the ONU. So the OLT part is as it is, the tech profile, the bandwidth profile, everything remains the same. The gem ports and alloc IDs, which were already allocated for this ONU, remains the same. It's just that the ONU is configured. So this reduces a lot of call flows, lot of DB operations, lot of to and fro, lot of event handling. And also it's quicker because we don't have to go through all of these things. And it has served this purpose of reducing resource consumption across the VOLTHA stack. And yeah, that is on the new reboot optimization. And one more important what we have done is the memory footprint reduction across the stack. So the main memory consumption was done by the ONU adapter. If you can see here, these are the numbers for 24K ONTs or 24K subs, HSIA configuration basically across 3 VStacks. Now VStack earlier already explained what's a VStack. So we have spread 24K across 3 VStacks. Now 2.12 is what the ONU adapter consumption was. It was almost 22 gig for 24K. With 2.13, it's 5 gig only. And if we take the full VStack consumption, VStack including all adapters and the controller, we were at 31 gigs. Now it's at 13 gigs. So this is like almost 70% reduction in memory consumption, especially for ONU adapter, and almost sort of 50% across the stack. We did reduce across the stack, but it was not so much as we reduced for the ONU. The ONU adapter was a bigger chunk. So this has quite reduced the footprint and has allowed us to scale even more on a pod, considering a 3-node cluster if we consider. Next is on option for offloading the apps. So at times we would need, because the functionality of offloading, the IA functionality and the RIA functionality are already available in the OLTs. So for resource considerations in the pod, so we introduced an option for the controller to offload the IA and RA functionalities to the OLT. So with this, we keep the circuit ID and the remote ID as part of these configurations, and the OLT itself will do the IA and RA instead of trapping it to the controller. Yeah, although it's an option, you can have it. It's an optional optional feature. You can choose to have it or not. You can still go ahead and trap to the controller and ask the controller to do it. And also we can have this offloading to OLT. So all the interfaces are well defined, the parameters are well defined to offload the parameters to the OLT. Another we have enhanced the DMI is for the line cards, especially the chassis-based ones, wherein we need to operate on the line, disable, re-enable, or reset the line cards, or also if you want some alarms on the line. So the device management interface is well defined for these events and operations. Moving on, what is next? After 2.14, we have some things on the line, which is ONT deactivate. This is at the PLOM level, wherein we can put the ONT to a state wherein it will start or it will stop participating in the ONU. So this is disabling and enabling it at the PLOM level. So this is in progress. The interfaces are being defined in review and will be part of the upcoming release. Next another one is on updating the device configs, especially the OLT and IP address for now, IP address of the OLT. So there are situations wherein an IP address of an OLT can change because it's being moved across or because of some topology change or whatever. In that case, we would need to change the IP address in the controller as well, because as of now, the controller is sticky, it has stickiness to that IP address of that OLT because it has been running a session which is connected to it. Now we'll have to reset the session, change the IP address. So that is where this feature will be. So this also will be part of the coming release, wherein the changes are across the interfaces. We have changes in interfaces, in the core, in the adapters, and in the agent as well. That's all. I think so on the feature list, what we did for 2.14 and what is there going forward in 2.15. Now going on for VOLTHA, where it is deployed in production. So we already have it in first live deployment in DT, wherein we are already handling a few hundred subscribers, and the target is to thousands by this year and more than 10,000 over the years. And also it's deployed well before and also in scale at Turk Telecom. And I think so Turk Telecom, it's already been running from quite some time. And in Reliance Jio also, it's already running in the production, but there are some trials also running. It is a bit of different sort of VOLTHA there, with a bit of modification. And there are other vendors which we are evaluating, and it's in very early stages of field trials or POC stages, wherein VOLTHA is being used. Moving forward for the community contributions and for all documentations and project page. So here it is. If we want to know about the left broadband and all the documentation, what all we need for the VOLTHA is there here. And if any contributions, how to contribute is there, the page. We also have a mailing list. If there are any questions, open questions, or any problems, or any issues which anyone faces during their testing, we have a group. We have a group for TSTs only. And we also have a Slack channel wherein if anything immediately required, we can get in touch and chat up. And also we have a Jira wherein you can report issues. If you see any issues that would be helpful, it would help us to fix and make the work stable. And also we have TST meeting, I think so bi-weekly Tuesday at 8 a.m. That's time. And this is the community as of now. A lot of them are in progress of getting in. That is in progress. Yeah, that's all I had for today. Thank you. And I think so. I'd like to take any questions. Anyone have any questions?
I think we don't have. Maybe I can ask a question, Abhilash, regarding the memory consumption. So we now have a better system in terms of memory. What is your, in terms of CPU, are there any improvements too?
CPU, we are working on it. We didn't see much wherein we need to improve, but we have made a couple of improvements. Shortly, we will share the code for review.
Okay. It's great to hear. Thank you.
Yeah. Out of the profiling, we didn't see anywhere we could improve drastically. Okay, there were here and there small, which wouldn't matter much, but nothing very concrete or nothing like a big chunk wherein if we'll get some 30% reduction. Yeah, we did reduce our 10 to 20% now in core, and fix is on the way. We'll share it short.
Okay, great. Thank you. I think we don't have any questions and we can close.